A Huawei Ascend 910B accelerator card, pulled from a Chinese cloud rack in late 2023, sits on the teardown bench with its package intact and its die still hidden beneath layers of integration. TechInsights photographed it. The images are public. What the surface presents is a large, dense slab of logic surrounded by memory and enclosed in a server-grade package, and that description is accurate as far as it goes, which is not far at all. The surface of a chip is the least informative layer it has. Every layer beneath it carries more weight than the one above, and the deepest layer of this particular object carries a weight the surface does not prepare you for, because the deepest layer encodes the restriction that was supposed to prevent the object from existing in its current form. We are going to open this one chip, pass by pass from the outermost packaging down to the process node, and at each level the same buried fact surfaces in a different form. The export constraint that was meant to stop this die is the reason its inner architecture looks exactly the way it does. The cuts run through node and patterning, then compute fabric, then memory stack and bandwidth, then packaging and interconnect, and they end on the parts that still had to come from outside. The first thing you see when the 910B card arrives on the bench is its form factor. The card is sized for server rack deployment, physically comparable to a high-end server accelerator, and it ships in a configuration that TechInsights Imaging identified as a multi-chip module. The logic die and memory components are integrated at the package level, rather than fabricated as a single monolithic piece of silicon. This is not an unusual approach in advanced artificial intelligence accelerators. Nvidia's own products use similar integration strategies, placing different functional elements on different dies and connecting them within a shared package. What is distinct about the 910B's packaging is that the sophistication it demonstrates is partly compensatory. A leading-edge process node would allow more functionality to be placed on a single die at higher density, reducing the need for complex package-level integration to extend the chip's reach. Here, the package is doing work that the process node cannot do on its own. The form factor tells you the deployment context. The package tells you the engineering strategy. Neither tells you the process, which is where the constraint lives. Peel back the package and the die declares its node. TechInsights reported that the Ascend 910B die was fabricated on SMIC's N+2 process, which SMIC positions as a 7-nanometer-class node. Independent analysis, including TechInsights' own characterization, places the effective transistor density below what TSMC's 7-nanometer node achieves, and substantially below the 5-nanometer and 4-nanometer nodes on which Nvidia's H100 is produced. The node gap between the 910B and a current Nvidia flagship is, by the teardown's evidence, at least one full process generation, and arguably closer to two, depending on the density metric used. The reason that gap exists is not a matter of engineering capability at the design level, it is a matter of equipment. SMIC fabricated this node without access to ASML's extreme ultraviolet lithography systems. Those systems are subject to export controls. SMIC therefore patterns its leading node using deep ultraviolet multi-patterning instead. Multiple exposures per layer, tighter process control at each step, higher manufacturing overhead across the whole production run. Multi-patterning with deep ultraviolet light is slower per wafer, less yield efficient than extreme ultraviolet patterning at the same node target, and operationally more complex. The company's own claims about yield on this process are not independently confirmed. What is confirmed is the patterning method, and the patterning method is a direct imprint of which equipment was available. Every transistor on this die was placed using a process chosen because the preferred process was unavailable. The chain from export policy to silicon is short and entirely legible in the die's own structure. The next layer down is where the chip's core function lives. Everything above it is packaging and process. Everything below it is memory and communication. The compute fabric of the 910B is centered on a large matrix multiply-accumulate array, consistent with an architecture that prioritizes raw throughput at lower numeric precision, which is the operational profile of a training and inference accelerator for large models. Huawei's published specifications claim peak performance figures in 16-bit floating point and 8-bit integer formats that are, on paper, within competitive range of Nvidia's A100, the prior flagship generation. The company's own stated figure for 16-bit brain-floating point throughput falls in the range of roughly 256 to 320 tera operations per second, depending on the configuration cited, and no independent benchmark has confirmed sustained throughput at that figure under realistic inference workloads. The compute tile, as imaged, shows a matrix unit array that is architected wide rather than deep. There are more lower precision matrix units spread across a larger die area than you would expect from a chip built on a leading-edge node. This wideness is the engineering answer to the node constraint, and it is worth stating clearly, when you cannot shrink, you spread. A 7-nanometer-class die is physically larger for the same transistor count than a 5-nanometer die. Reaching a competitive peak throughput figure on a less dense process requires placing more compute units across more area. The 910B does this. The result is a die that approaches the A100's published peak figures through area rather than through density, which is a legitimate engineering answer with a cost that appears 2 layers deeper. A larger die is harder to yield cleanly across a wafer. It consumes more power per unit of compute relative to a denser process. It generates more heat under load. The thermal behavior of the 910B in sustained workloads is not publicly benchmarked in detail, but the architecture makes the physics entirely predictable without a benchmark. The memory layer is where the 910B's limitations become quantitative rather than qualitative. The chip uses high bandwidth memory in its reported configuration. TechInsights and supply chain reporting identified high bandwidth memory components in early production units. Subsequent reporting raised questions about whether all units across the production run used high bandwidth memory, or whether some units used alternative memory configurations as high bandwidth memory supply became constrained by a separate and later round of export controls applied specifically to high bandwidth memory sales into China. Huawei has not publicly clarified the memory configuration across its full production run at a granularity that allows independent verification. The company's published bandwidth figure for the 910B is approximately 900 gigabytes per second. The H100's published bandwidth is roughly 3.35 terabytes per second. That ratio, approximately 1 to 3.5 depending on configuration, is a material gap for memory bandwidth-bound workloads, which describes a substantial fraction of large language model inference and a meaningful fraction of training. The gap has 2 sources. The first is the high bandwidth memory supply constraint, which is itself the product of controls applied after the 910B's initial design was already underway. The second source is structural to the die itself. A larger, less dense process node leaves less physical space adjacent to the logic die for memory interface circuitry. The memory bus width is constrained by the die area available to the memory controller fabric, and the peak bandwidth is constrained by the bus width. The chip's architects knew this before tape-out. The response to it is encoded in the next layer. The interconnect layer is where the 910B stops being a component and becomes a system. Huawei's published specifications for the 910B include a high-bandwidth card-to-card interconnect for multi-card and multi-node configurations, marketed under Huawei's own interconnect branding. The company claims aggregate cluster bandwidth across large deployments sufficient, on paper, to compensate for the per-card memory bandwidth constraint by allowing the memory of many cards to function as a unified distributed pool. The scale-out topology in Huawei's Atlas 900 and Cloud Matrix cluster deployments uses this interconnect as a load-bearing architectural element rather than a supplementary one. Independent performance benchmarks on these clusters for large model training workloads are not publicly available as of this analysis. What the interconnect layer reveals about the object is this: the system architecture was designed around a die-level limitation. If a single card cannot match the memory bandwidth of the H100, a tightly coupled cluster of 910B cards can distribute the memory requirement across a larger pool, provided the interconnect is fast enough and the software stack can address distributed memory efficiently. Scale-out networking as a primary architectural response to per-card bandwidth constraints is a real engineering philosophy, and it has precedent in how large-scale training systems are built regardless of the accelerator used. The question the die itself cannot answer is whether the software stack that exposes this distributed memory to model training and inference workloads, Huawei's CANN framework, and the associated compiler toolchain, is mature enough for the full range of model architectures that researchers and practitioners bring to it. Software stack maturity is not a teardown observation. It is a deployment history, and the deployment history of the 910B at scale is not yet documented independently at the granularity that would allow a conclusion. The deepest cut is also the most carefully hedged because the evidence at this layer is partial and the company has not disclosed a full component manifest. TechInsights and other teardown analysts identified components at the package and board level in early 910B units that carried markings consistent with non-Chinese suppliers. These identifications included components in the high bandwidth memory stack and in certain passive and power management components. This is the layer that the surface of the chip does not show. The logic die looks complete when you image it, and at the logic level, it is complete. The identified foreign content sits at the boundary between the die and the system, in the memory stack, in power delivery, in components that are invisible until the package is opened. Subsequent export control tightening, specifically controls applied to high bandwidth memory sales into China, after the 910B's initial design was committed, complicated Huawei's ability to source these components at scale. It is not publicly established what proportion of later production units use fully domesticated memory or power management components, or what performance trade-offs, if any, accompanied those substitutions. The logic die itself, the compute fabric, the interconnect circuitry, the memory controllers is a SMIC fabricated Huawei-designed product. The identified foreign content sits at the integration layer, not the logic layer. That distinction is the most precise thing the teardown establishes about the 910B's current state. The deepest layer reveals something the teardown reports note but do not synthesize into a single sentence. The restriction that was meant to stop this die did not stop the logic layer. It stopped the process node from reaching leading edge density, and it eventually stopped the memory stack from being fully domesticated on the original schedule. But the logic layer, the compute fabric, the interconnect, the memory controllers, is a genuine engineering product on a genuine domestic process. The 910B's logic die is not a copy, not a workaround in the pejorative sense, and not a placeholder waiting to be replaced. It is a competent, production-grade, artificial intelligence accelerator logic die built on a real, if constrained, process. The gap that remains is real and measurable, but it is located in different places than the restriction was designed to enforce. The original restriction assumed that without access to TSMC's process, a competitive logic layer could not be constructed. The teardown shows that assumption was incorrect. The gap that persists is concentrated in memory bandwidth, in memory supply chain access, in yield efficiency at an immature leading edge class node, and in the maturity of the software stack. Those are real constraints. They are not the constraint the policy was built to enforce. Consider the logic die as a precision machined engine block. The block itself is a domestic product built on domestic equipment by domestic engineers to a competitive specification. What remains partly sourced from outside sites at the integration boundary, the memory that bolts onto the logic and without which the compute fabric cannot move data at the rate the workload demands, the power management components that regulate delivery under load. The engine block is domestic. Parts of the drivetrain are still sourced. This is the distinction the 910B encodes, and it is the distinction that the export control regime has been chasing since the teardown made it legible. Three things the dissection cannot settle deserve plain statement. The first is yield and production volume. The 910B performs on the teardown bench as a chip that reached the teardown bench. What proportion of wafer starts on SMIC's N+2 process produce functional dies at this die size using deep ultraviolet multi-patterning is not publicly established. Yield at an immature leading edge class node patterned with multi-pass deep ultraviolet exposure is structurally harder than yield at the same node using extreme ultraviolet. The company's production claims are company claims. No independent supply chain analysis has confirmed volume at the granularity that would support a cost per effective compute operation comparison with Nvidia's production economics. The second unsettled question is sustained workload performance. Peak figures are company figures. The teardown reveals architecture. It does not measure what happens to throughput under memory bandwidth saturation, thermal throttling, and the software stack's handling of real model architectures over extended training runs. No independent benchmark of a large 910B cluster, under a standard large model training workload has been published as of this analysis. The third unsettled question is the foreign content question at the production lot level. Teardown sample individual units from a production run. Whether the identified foreign components in early units have been substituted in later production and at what cost to performance or yield is not publicly established. The trajectory is toward domestication at this layer. The current state of that trajectory is a company claim rather than an independently verified fact. Taken together, the dissection establishes the architecture and the node with reasonable confidence, identifies foreign content at the integration layer as a teardown observation rather than a production-wide conclusion, and cannot resolve yield, volume, or sustained performance, which are the three variables that determine whether the gap is closing at the speed the surface narrative suggests. The 910B, opened layer by layer, proves a specific and limited set of claims. It proves that the export control regime as it existed through 2022 and into 2023 was not sufficient to prevent the construction of a competent artificial intelligence accelerator logic die on a domestic process. It proves that the gap between this die and a current Nvidia flagship is real, measurable, and located in specific places: the process node, the memory bandwidth, the memory supply chain, the software stack maturity. It proves a third claim that the teardown reports do not state outright. The shape of the gap has changed. The gap the restriction was designed to enforce was a logic layer gap. The gap that now exists is increasingly a memory and system level gap, and the restriction regime has been adapting to chase it to those new locations. The die proves that the chase is ongoing and that neither side of it has found a stable position. Cut deep enough into the 910B, and the constraint is present in every layer: in the node, in the patterning method, in the memory architecture, in the scale-out philosophy that compensates for bandwidth limits at the card level. But the constraint is not the conclusion. The conclusion is what the engineers built around it and what that building reveals about where the actual frontier of the gap now sits. The 910B does not close the gap with Nvidia's current generation, and the teardown does not show a chip that claims to. What it shows is a chip that has moved the gap to a location the original restriction was not designed to defend. The next object I want to open is the one you think the teardown community has not looked at carefully enough. Drop the component, the system, or the process in the comments, and the one that reveals the most that the surface obscures is the one we open next. Subscribe if you want to be at the bench when we make the next cut.